but my computer crashed.
You have our full attention now.
Yes. Attention, please.
Thanks, Ernst.
It crashed my computer twice, which is very unusual. Usually I reboot like, I don't know, twice a year or so. So anyway, so I'm Ernst Niebur, I'm at Hopkins, and I've been, as Malcolm, I heard, I've been working on attention for quite a long time. Actually, in '97, when I was here the first time, I already worked on that. I had already moved to Hopkins, so this work was started when I was a postdoc at Caltech with Gustav Koch, and I'll refer to that later. So important. This is okay. This is first. Let's see. It's the overview. So what I want to do is I will spend quite a bit of time on motivating, explaining what attention is, and motivating why it is so important. Since it's important, I hope I can convince you of that. We, as computational neuroscientists, which I'm one of, we want to have quantitative models. I mean, of course, people have thought about abstract models of attention for a long time, mainly psychologists, but we want to have something quantitative. We want to have something that we can run on a computer, that we can test, that makes predictions that we can test. We want to have methods to test them, just a quantitative way to approach it. And then, so I talk about one or two of those models, one going way back, and the other one, which is actually the, I pointed, right? The other one, which is actually the by now, much better model, I think, has some features that I would love to talk about, but I graded out because I think I don't have time to talk about it. Instead of doing that, I will talk about newer work where we, particularly for this audience, how we do this. Can we do this in a kind of a native, neuromorphic way? Get a model of, if you want, even a hardware model of saliency computations. And I'll talk about saliency also in a second. Okay, so that's the overview. And so this is an important slide that I've been using for many years. So apologies to Malcolm and the other people who have seen this before, but I think it's important because I think it brings home the point that how essential selective attention is, and I get back to that in more detail than in previous years in the following slides. So what it's a function. What is the function that this that is a problem that this function is designed to solve? Well, it's very straightforward. It's information overload, and this is not something, I don't know, or TikTok videos or something like that. But the latest generation is spending a lot of time and attention to. This is a many hundreds of millions of years old problem because any organism that has certainly has the central nervous system, maybe even before that, needs attention to sift through the overload of information that is coming in at its senses. And so to give, yeah.
So you use the word sift.
What?
You use the word sift, which implies an active process of picking and choosing what you want to do, as opposed to I'm single-minded, focusing on you.
Yes.
And I could care less what else is going on.
Yes.
Do you think sift is the right word?
Yes.
Okay.
Filtering, sifting. Actually, I usually used to use filtering, but now I talk quite a bit about a new paper that came out earlier this year, and they don't talk about the filtering ratio, which is the ratio of the information that comes in and that you actually use, and they call it sifting ratio. And so I think I see it in the same way. I don't know. Is this you? Why you're asking?
Because I've been thinking a lot about how, it's not so much that we're shifting, it's like I'm actively looking for information at you to figure out what you're saying next. So I don't even know the other stuff going on. It's not even going anywhere. I'm completely focused on my attention. I mean, my model is, and maybe you'll tell me, hopefully you'll tell me I'm wrong. My model is focused on getting information from you that help me form my hypothesis about what you're saying. And so it's more of an information gathering paradigm than it is a bottom-up filter.
Well, okay. So there's maybe there's bottom-up attention and there's top-down attention, and both are important. And I talked a little bit more about that later, but just to answer this question, I mean, yeah, you certainly, your top-down attention is direct on me, hopefully it's the case for everybody. But if there were some big flash outside, I mean, an explosion or something like that, immediately everyone would turn, at least mentally, and direct attention there. So, that's just one example that changes it, but there's many other things that are going on. I mean, something not that dramatically, but I mean, while you're filtering your attention on me right now, what your left-hand neighbor is maybe scratching his head or something like that, that is filtered out. Okay.
Yes, it's frozen. It doesn't work, so we need to reshare from here. Let me do it.
What?
It doesn't work. Like I tried again, but it doesn't work.
Oh, okay, fine, okay. Yeah, so I'm not going to give my LibreOffice PowerPoint-like talk. This is PDF sort of limitation, no videos and stuff like that. So, well, again, we want to do quantitative things. So when I talk about information overload and the fire hose of sensory input that we are exposed to, can we quantify it? And yes, we can, but it's actually very simple. So let's talk about vision. Many people work on vision, and it's not very well studied, so do I. The retina has 1 million each eye has a retina, and each retina has the only output from the retina to the brain is through the retinal ganglion cells, which is the last stage, and it's the only neurons that spike in the retina and that communicate. So all the information goes through this bottleneck, and there's 1 million cells in there. So how much information can they transmit? Well, a neuron, a self-respecting neuron, has something, the firing rate of a self-respecting neuron is like maybe 10 to 100 or something like that. Okay, sometimes they can, or sometimes they fire like crazy 200 or so, but they can't fire whatever at the kilohertz or kilohertz, things like that. So let's take a round number, let's say 100, and we have 100 spikes that may occur or not every 10 milliseconds, or maybe a spike or not. So that is a yes/no decision. That's a bit. So we have 100 bits per second. We have 1 million neurons. So we have 100 megabits per second per eye. Okay, and the same argument applies to the same number. Actually, a pretty similar number applies to the somatosensory information, the tactile and itch and pain and all that. That's about the same number. And then you have auditory, which is lower, and you have internal and receptive. So that's a bit more. So it's on that order of magnitude, like a gigabyte or a fraction of a small fraction of a gigabyte, a gigabit times per second, okay, which is a lot of information. And so this is much more than we can compute on and process in our central nervous system, and I get a lot more detail on that in the following couple of slides. So what we have to, the problem that selective attention solves is to sift or filter out of this huge amount of information, that is important. So hopefully at this point it's me talking, but then maybe it's other things that intervene, and so then your attention will shift to something else because your system decides that it's more important. So oh yeah, and this is was just my whatever back of the envelope calculation. Turns out you can, of course, information theory is very much more quantitative than counting the numbers. So you look at the distributions of well, I was looking for my power cable. Okay, if you compute the distribution, then it turns out that when people looked at that in all kinds of systems, from flies to mammalian cortex, it is on the same order of magnitude if you really look at the exact numbers. So so this is one slide that sort of it's stealing my thunder right away. So this is the question is, so we know what the input is. It's on the order of a gigabit per second to the whole organism. What is the output? And people have asked me this before, and I looked up. There's a paper nearly as old as I am, from the mid-50s, when the psychologists discovered information theory, and there was some guy who measured the information capacity of a skilled piano player just by the probability of pushing the right keys of the piano on the keyboard, and that was on the order of, yeah.
Sorry, remote lost screen share, I think.
Again.
It was working. That works fine.
Okay,
It's
now
fine.
it's back. Thank you.
Okay. Okay. Anything else to do, or
No,
just
no.
to yell at you?
Yeah, no, just, yeah.
Okay, thank you. Okay, so what this paper about? It's not even a journal. It's some book that is that you can find in the reading library. That was on the order of 100 bits per second. I think it was 80, 85 or something like that. Completely ignored by the literature. So there was no, as far as I know, there was no really good answer to that. Only that it must be a lot smaller. So fortunately, this year, Marcus Meiser, who some of you may know, he did a lot of work on retina at Harvard, and now for a couple of years he's at Caltech. He wrote with his student Zhang, I think is his name, a very nice paper. And what they did is they addressed exactly this question: what is the output of in terms of information throughput of a human being? And so now this was supposed to be a Peer 1 at a time, but well, doesn't work. I'll show you more. So the first thing is they did a very similar thing. They didn't do anything actually. This is all literature research, just putting things together. So they looked at a paper that none of them had thought about attention or something like that. They looked at a paper that measured the output of a skilled typist, and you know that you can type very fast, but you have to take into account that there are very high irregularities in, for example, English language. So you look at the probabilities and all that. So information theory gives you the output of a skilled typist is on the order of 10 bits per second. Okay, that's the output of a skilled typist. Very far away from the information that the person is getting when they're copying a text. For example, if they're reading, there's 100 megabits per second coming in through their eyes, but the output from their fingers is 10 bits per second.
And the megabits is what comes to the retina, or at the end of the retina, what goes to the LGN?
At the end, what goes to the brain. There's already a reduction of about 10 to 100 from within the retina. I mean, and that's very easy because the rods, there's 100 million of them, and the output is only 1 million. So that's it. But I mean, Meister says it's more like 10, because there's not every single cone has necessarily information by itself. But let's not get into that too much. So, but there's already at least a 10 reduction of information within the retina. Okay, so you might say, well, of course, our muscles are slow, right? We are clumsy, so maybe that's a limitation. So let's look at a channel that is designed to have for communication, and that is what I'm doing right now. Speed talking, giving a talk. So what's the information contents there? And what it turns out, people have. So if you talk to people that train, if you talk to trainers of people that give talks, I think it's 160 words per 100 or 120 words per minute. This is a good rate of transmitting information, because otherwise, if you go too fast, you can't do it physically. That's a motor problem. But also, if you talk really fast, you can't. The audience is not going to be able to follow. Yeah.
Do you think this is interesting? Because I don't think it's very interesting. It's obvious that any classifier is going to have a lower output than input. You know, and it's obvious that you need more than 1,000 distinguishing things per second to actually control all these muscles.
Okay.
You need a lot more bandwidth there than that.
Actually,
right? It's not that interesting. It's like saying you have a CNN, the output is cat or not cat.
Yes.
The input is millions and millions of pixels.
Okay, so
why do you consider that remarkable?
I think it's remarkable. Not the motor part is less important. It's less important. But this is not only the motor part. This is a part, everything that you do, the thinking. The thinking is limited by
the output. In the end, you need a low dimensional output, right? So
no. Why? Why?
But I'm saying that this is undercounting the actual signals that are required to do all this typing, all this muscle control.
Yes. No, but let's forget the muscle control. Okay, let's think about thinking. Okay, that is cognitive tasks, and there's a few of them, and I can if you think it's not interesting, we can.
But again, why do you think it's interesting that the output is low dimensional?
No. But so what is the brain doing? For example, if I am
Deciding stuff.
Deciding stuff. Very good.
Yeah. So.
Let's see which memory foam speed cards. Okay.
Planning.
Okay. Let's learn. Okay. Let's jump to the last one. So that requires less explaining what is done. So they have a whole bunch of tasks that they do, and I picked the 5 of them or something, whatever it is. But the last one, I don't have to explain anything. They're all very impressive, I think. But the last one, I don't have to explain anything because it's something probably every one of you has done it. And that is the game 20 questions. Okay? So let's do a controlled version of it. Let's say I give you 2 seconds to think about something. And then we play the game 20 questions, so you know what it is. There's 20 questions that I can ask you after you've thought of your idea, and then if I get it with 20 questions, then I win. Otherwise, you win. Okay. So if you do it, think about for 2 seconds about something. 1, 2. Here we go. Hopefully, everybody now has an idea of what you want me to ask you about, and then I do my 20 questions. Well, these are yes/no questions. Okay. So it's 1-bit information. So there's 20, and so there's the 20 is not arbitrary. I mean, it's if it were 2 questions, probably it would never work. If it were 200 questions, it would probably always work. So this has been established that this is something where in the sweet spot where sometimes you win and sometimes you lose, because otherwise the game would not exist. Nobody would play it. Okay, so with about 20 bits, I can guess what you just thought about. So 20 bits is a million things, which sounds like a great number. It's 2 to the 10, obviously, right? So it's a million things that you can go through in your head at the maximum in 2 seconds. Okay, so that's 10 bits per second. Okay, and this is something that is not constrained. There's no motor action involved or something like that. That is really the thinking, and that why is it? Well, it's a game, of course. But for example, if you play chess, it is known that even the whatever grandmasters, what the next stages are, I mean, they do things serially. They follow one thing, and then they evaluate the value of that, and say, okay, this is not good. They go back, try another thing, until they find the most the optimal thing to do in this situation. If we had the capacity like we have in our model systems, very, very complex things, we can do the same thing. I mean, like unconsciously working over a tricky part, you have a lot of very detailed muscle activities that you generate, but you don't think about them. Maybe when you're learning to ride a bike, maybe you use the thing, but in the end, you do very complicated things also at the output, probably at the same order of magnitude, but in between, you have this bottleneck. You do, instead of a million different things exploring by on the chessboard, which would give you certainly a big advantage compared to your competitor who has to do one thing at a time, go 5 steps forward, decide it's good, no or no. If you could do a million things, or 10 million things, or 100 million things, you would have a huge advantage. So that is like trajectory planning, all these things. Does that make sense?
Not entirely, because I mean, when you're exploring this path, you're also essentially exploring many paths, right?
No.
Finally, you go down one path, but you're deciding, you're classifying at every stage when you're planning a sequence of moves In chess, at every point, you're making some decision.
I don't think that's true. I think you do really one thing at a time.
Yeah.
Try to not let's do stress. Let's think about if you go whatever. If you go you plan what you do this weekend. I mean you say, okay, I could go whatever. Go
Everybody's imagining sleeping, eating.
Yeah, well, I mean, but you do one thing at a time. And all of these, I mean, these are only 5, and there's like, as I said, 10 or 20. There's a whole appendix on that on the different tasks of all different things. I mean, perception is another thing. I mean, that it's limited by its very, very low capacity.
I also objection from Germany.
Yeah.
Are you talking about what you're consciously aware of that you're doing? Because there is a lot going on in the background. So you're thinking. Chess is thinking slow. There's thinking fast, and then there's way bigger is thinking unconsciously.
Yes.
So how does that figure in?
Okay, so 2 things. One is there's certainly unconscious things that go on. For example, as I said, in the motor nervous system, but that in the peripheral motor nervous system, you have all these reflexes that come on, and that you have no idea what's happening. I mean, one example. I talked to somebody the first day I was here. So if you're standing here and you decide to lift an arm. What is the first muscle that gets activated? Well, you say something in the shoulder. It's not. It's a muscle in the leg because you and you never would have thought about it. I certainly didn't because you compensate for the difference in the forces. So certainly in the peripheral system, there's a lot of unconscious things going on, and people have claimed that this is also the case for memory, for storing into memory and all that. But and one prime example is photographic memory. So people say there are people that can take a page in and within a second or a couple of seconds have everything, pretty much every pixel memorized in that. That is not true. And they Meister and Zhang address it. That is okay, I don't want to go into detail, but they have arguments that is not sustainable. So there's certainly many unconscious things going on, but they're all at the level of not at the level of what we perceive as a cognitive. Yes, you're right, conscious activity. Does it address?
Go ahead, yeah.
Okay, yeah. Let's. Okay. Anyway, I think we. But yeah. Okay, let's go on, please. Okay, so space. Don't tell me I crashed this computer.
No, click over. Some sort of malediction today. What's going on?
I think it's ready to type for some reason.
It's killing me.
Disable.
Thank you. Okay. Okay. So okay. Let's go with the flow. Okay. Let's we can talk later if it's true or not. But let's go with it. Then there's a gigantic filtering thing. Actually much bigger. I mean than also I thought. So it's a ratio of 10 to the 8. And so what Zhang and Meister say, and I think I agree with that, it's the largest unexplained number in brain science. Gigantic number. And back to the topic of this talk, they acknowledge that one of the most important parts of that is filtering by attention. There's certainly others, but this is certainly one of them. So, why can we get rid of this? I don't want the assistant. What is the assistant?
I don't know, maybe let's try to just remove it.
Yeah.
It goes away.
Zoom wants to assist me. I thought this is much better, yeah. Thank you. Okay, so by the way, the paper is the title is The Unbearable Slowness of Being. Why do we live at 10 bits per second? And it's a pleasure to read. I recommend it. It came out in Neuron in January. So Okay, good. Having this established, so there is, and this is by no means a new idea. I mean, psychologists, at least since the 50s, and in a way since William James in the last century, have acknowledged that there's a bottleneck in the brain, and that's why we need attention. We cannot process all of that, and therefore we filter. But it's a very valid question. I mean, that again they figured mastering up. What is really the bottleneck? And I'm definitely not going to do that into the question, but it's not obvious really, at least to me. And what are the resources that are limited in that? So if you don't believe me, let's do a little experiment. So it's a classical experiment. It's 40 years old, but I like it. So there are three parts to it, and I show something on the screen which has always a bunch of distractors, which are green lines and green vertical lines, and there may or may not be a target, and you have to tell me if you see a target. Okay, ready, set, go. Okay. Anybody didn't see a target?
You see the red vertical thing.
Yeah. Yes. Yeah. Yeah.
But
That's
that
a target.
makes the colorblind ones.
Maybe I shouldn't use.
How many
You're
people
right.
are red being colorblind in this room? Is
I don't know,
anybody?
but 10%
Yeah,
of
2
the
out of-
population do. Yeah.
Okay, I should change it. You're absolutely right. No, yeah, you're right. But just for interest, did you see it? The difference, John? Did you see it?
I saw it.
No, you didn't. Okay, well, I saw a minute later. It's okay. So, okay, I expected it. Thank you. Okay, now we do the same thing. This one is for the colorblind. Now we have a difference in orientation. Okay, so the target is always the same, red vertical line, but now the distractors are also red, but they are horizontal. Okay, so 1, 2, 3. Okay. Everybody saw it, right? Okay, good. Now you're trained observers, as we say in the field. So the next is, and there's no trick. I mean, not cheating or anything like that. I mean, what the next one is we have been trained on the two types of distractors. Now we just have both type of distractors intermingled. Okay, but the target is the same, task is the same. Okay.
So the two have to co-occur.
What? Say again.
The distractor, the vertical and the horizontal have to co-occur, be together.
No. That's,
All you have to do is say if there's a vertical line.
yeah.
That's all.
And I mean, there's this red horizontal and green verticals. They're all spread over the whole screen like before. And
Right.
the target may or may not be there. Okay, ready? 10 goes. Okay. Anybody seen it?
No.
That is surprising. Maybe. Okay. Yeah. In a crowd of this size, I would expect 2, 3 or 4, something like that to see it. Okay. But I think we agree, and again, there's no trick. I mean, these are the stimuli, and this is exactly what I showed you, the very stimuli that I showed you. Well, of course it's there. Okay, I treat it in the sense that I told you there may or may not be one, but for simplicity, I don't want to do it 10 times. So there was always a target, but it was not as easy to be seen in the first and in the last one. So what's the difference? So as I said, this is 45 years old. Treisman and Treisman designed the start. It's called a Treisman task. So there must be something fundamentally different. If there's everybody thought for these two things, and then I just lingered them up, and then there's maybe one that didn't see it. So what's the difference? Well, in the first, that is called a pop-out task, because that is actually a technical term, because I'm learning here. Because this target here pops out in its environment, it pops out here, but it does not, where is it? It does not pop out here. Why is that? Well, and Treisman's explanation was that the two easy tasks, the difference between target and distractor is in one dimension, in color in the first, in color in the second experiment, and in the orientation in the first experiment. And while here, it's a conjunction task, so you have to know both. You have to use both the color and the orientation, the shape, to distinguish the target from the distractors. And she was a psychologist, not a neuroscientist, but she thought about why that could be. And the idea is that, and that was her hypothesis, that we may have filters that that can work in parallel, because the filters are replicated over the whole visual field, that can detect one dimension only, color or orientation, and maybe some others. But if you have to combine these filters, then well, there's many different combinations. If you have 5 different filters, then you have a large space of possibilities. And her hypothesis, and I think that one is true, is that you cannot afford to replicate all these combinations in all places in the visual field. So therefore, you have to do something different, and that something different is you have the filter. You can do the task clearly if I give you enough time, and I'll show you on the next slide how the time evolves. But you cannot. You have only one of them, and so what you have to do is you have to do a serial search for the candidates. And if you do the task, and so she did it properly, conservatively, and all that. So what is shown here is the display size is the number of distractors, and on the vertical axis you have the reaction time in this very task that we just did. And what you find is, well, if you have a feature target, which is at the bottom here, then the reaction time does not depend on the number of distractors. So if I fill the whole wall here with green things, and there's one red, you will find it even if half in the same time as if it's only a much smaller part of the wall. Okay. On the other hand, if you have the conjunction task, the reaction time goes up linearly, interestingly, with number of distractions. Here they go up to 30, and there's gaps in between, but this task has been replicated probably 1,000 times in different labs and different variations, all that. So it's really a very linear function, and that is exactly what you would expect if you go through the visual field one item at a time, and then your filter gives your pattern detector gives you a yes/no decision. Yes, it is a target. It's not. It's no, 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 yes. And then if everything is randomized, so you expect that you get that when the target is present, you have exactly half the slope as if when the target is absent, because on average you find it after going through half of them. And so therefore your reaction time, this slope here when the target is present, is half of what you have when the target is absent, because the only way you can say with certainty that the target is not there is if you have exhausted all possible alternatives. Okay. And now I have to say, this is, again, 45 years old, and there's some things that this does not explain, and there's some subtleties, and there's some you can have more complicated things. You have only 2 features here. If you have multiple ones, there's other things appear. There's some clustering and all that. This is not the whole truth, but the main idea, I believe, is correct. What does this have to do with attention? We have the massive parallel input. We can process it all over the visual field for the feature task. We can process this in one step. But if we have to employ this dedicated receptor for the pattern detector for the more complicated cases, that is an attentive process. It means this is a serial process that we have to go through one at a time, and that is that is an attentive process that is limited by a bottleneck, by a pretty severe one. If you compare these, go back yesterday. If you compare these and you imagine it's 30, you have whatever 500, then it's a very, very strong limitation. Okay. Okay. So this is Anybody? Is everybody convinced that attention is important, that we have to filter? And yeah, okay, good. So okay, now let's look at the quantitative modeling part. So this goes back to paper by Christoph Koch and Theo Nollmann, but they were both postdocs at MIT. And just as a, if I don't know, that's how do I? If you're bitter because your paper didn't get into Nature, this is a good example. That's not that important. So it published in a journal called Human Neurobiology that only was published for 5 years or so, or 6 or 7, and it happened to be in 1985. And this paper was cited 4,000 times. So even if you don't get into Science or Nature, you maybe get credit later for your work. So anyway, so they said, okay, what attracts attention? And they said, well, there's two. Coming back to Markman's question, there's two things of it. You clearly can decide to focus on one thing, and that is called top-down attention. That is dependent on your internal state, on your interest, on your needs. But that is kind of difficult to study, and it's very complicated. Your memory, your history, what you had for dinner yesterday, all these things play a role. That's difficult to study. On the other hand, there are some things. I mentioned the explosion, or sometimes I do something down, so I jump up here. If I do that, that attracts your attention, and not only your attention, also if your cat is in the room, or your dog, or your monkey in a recording chamber, all this will attract your attention. So this is called bottom-up attention. It's purely data-driven. It is independent of what of your internal state. If your bee stings you while you're studying and focused on your work, if you have a bee sting, that will attract your attention. Okay, so this is bottom-up attention, and it's very much easier to study. So this is why they propose to start with that, and then most other people followed in that train. And can you address top-down attention? I don't know frankly yet, but it's not so complicated. So they said, okay, well, let's look at vision. So what attracts attention? Well, attention is something that is salient at a given time. Well, what is salient? Well, the red thing among green things was salient. None of the green things was salient because you were surrounded by other green things. If you wanted it's a somewhat advanced version of redundant reduction. You have lots of green things. None of them is by itself very important. If there's one red thing in there, it is. Okay, and then of course it's for color. Same plus occasionally did that. Motion is important. Something moving. Well, if it's moving not with many other things, importantly, but if it's moving countercurrent or on the static background, all these things are salient and they attract attention. And well, how do we combine it? Well, we just the difference between center surround is important. And you had a center surround difference because, as I said, something moving at high speed with many other things. Moving at the same speed and direction is not salient. It's only if it's different, so if local difference is determined whether it's salient or not. So we can do that. I mean, center surround architecture is very common in the nervous system. And then, but any of these can occur, so you have to combine all these things, and then you have salience in different, or conspicuity, we call it, in different submodalities. And then you can combine all of them and kind of integrate them and come up to a conclusion and to some maximum. I explain in the next slide how we can do that. I don't explain, I just stated. If you what that gives you, if you combine all these things, you get a two-dimensional, the visual field, a map from the visual field to two-dimensional field with a scalar value, and we call the value that we have, so the combination from all these different feature maps, we call that saliency. If you can do that, then your problem is 90% solved, because by definition, it's saliency attracts attention. So therefore, we have to find the maximum. We can do that when we take all, very common, both in neurology and in biology, it's all over the place. And then we have, if we find the maximum on this so-called salience map, we have the point where we attend first. Of course, we don't want to we don't want to find the right thing on the green background and stay there and stare at that for the rest of our lives. But you want to you look at it to say it's a target, it's not the target. You go to the next one, and that is again because this found that once you attend to something, then for the next couple 400, 500 milliseconds, you are less likely to attend to it again. It's called inhibition of return, and that gives a natural mechanism. So you attend to something, you look at an object that is salient, the most salient, that's a prediction, and then you process it, send it to whatever other detectors that you need, and then you go somewhere else, and somewhere else, somewhere else. You may go back to it after some time, but not in the first 500 milliseconds, and so on. So what this does, and I come back to the previous slide, what this does is you create a scan path, essentially, like where you're fixating at a given time. And this can be a scan path in over attention, meaning really your eye movements, or it can be the scan path of the covert attention, which is when you're fixating here, but you're attending to that or to that, and you do this all the time. And we know that this exists because I didn't emphasize it because I'm trying to get through this in a reasonable time, but the slope of the treatment task is 60 milliseconds per second per item. So you jump on the order of 60 seconds, you do an internal search for the next item, and that is what 5 or 6 times faster than your eye movements. Okay, so this, but in either case, you can generate this scan path either for eye movements or for the movements of covert attention. Okay, so going back to this, as I said, this was a concept was proposed in this very obscure journal and existed for the last 40 years at this point. But it was just an idea. I mean, of course, it's fundamental. So, as I said, I was in Christopher's lab. And so we looked at attention from a different point of view, but when I saw this, I was very intrigued, and I decided I wanted to make a model of that. And this is a model. So it's essentially what I put here, but it's essentially what I explained, just now coded in C++. And so you have visual scene, and then you have a filter bank of different channels, and we picked pretty arbitrarily. We picked color, color, intensity, orientation, but it's easy. You can add motion. We have by far many people have added some, including us. For example, depth perception is important. Texture is important. All these contribute. So these are just examples. So you have a filter bank of different submodalities that you have, and you have them at different spatial scales because small things can be salient or large things can be salient. And then you do so that these explains these different pyramids here. And you do a simple surround operation that I mentioned, and then you have these. You combine them again. In the end, you have to end up with one map. So you collapse all of those, and you do some normalization, which is actually important, but I'm not going to talk about it. And then the task is to put all these into one common map, the two-dimensional map that we label the saliency map. And how do we do that? Well, it's mathematically not well defined. What is red minus green combined with horizontal versus vertical, but the brain does it, we think. And so therefore there must be a way to do it. And basically what we do is we just add it, and in principle we could have different weights on these connections. And for example, it's a good idea to have that motion. We know it's about 5 times more important than color or orientation, but even if you don't do it, you get a decent output. And then you do the inhibition of return to get your scan path. Okay, so that's a computational model, and it's called salience map model, and it's being pretty widely used. One reason is because it's so simple. It's so simple, straightforward to implement. And in the later part, if I have a few more minutes, we can make it even simpler than what we did in this C++ program.
It's totally handcrafted, right? No machine learning at all here.
Absolutely, and that.
But nowadays there's machine learning.
Absolutely, but that's thank you for bringing this up. So that's exactly right. So and the performance of this, and as I said, there's many. We made, for example, we took into account objects. It's not only the features but the objects. So there's many variations on this model, but I don't think. I mean, probably. This model certainly not, and even the ones where we have the concept of an object, perceptual organization in there, even those they're probably not competing. If you look at benchmarks and competitive, if you look at benchmarks like from compared to these machine learning methods, but I think this is an advantage because one thing it's you don't have to do, to train from a very practical point of view. Whatever, 500 million parameters or 100 million parameters, whatever it is.
A small CNN can have all the parameters. You know, like 100K parameters.
The what?
A very small CNN can have all these properties. A very tiny CNN with just literally a few thousand weights.
Okay, a few thousand weights, fine. Let's say 2,000 weights. But this, I think, in this we are getting we're losing on winning on the benchmark competition, but we're winning inside because, of course, you can go back.
It's interpretable.
It's interpretable. And we get understanding from it. And of course, you can. I mean, what people like DiCarlo and then DiCarlo and other people, many people after it have done is you can look and you can analyze what your feed-forward convolution network is doing. But I mean, in this case, we have some parameters. I mean, like the sizes of the filters, the convolutional mass and all that. We have like maybe 10 or so free parameters, but we don't. And we try to get a reasonable output, but we don't train anything there because of that reason, because we want to understand the principle and implement the principle.
What I'm saying is if you did psychophysics, you did eye tracking, you had people look at thousands of images, you collect the eye tracking data, then you could easily train a few parameters or a few thousand parameters.
Yes.
You know, you constrain the model the way you understand. I mean, it must have been stuff done in that direction.
Yeah. But I don't know what the smallest network is that gives a comparable.
No, but I'm saying using eye tracking and in images, either synthetic, it must have been work after this, doing that, right? Was there work after that, trying to identify the importance of different features?
Of course, yeah. As I said, I mean, for example, that motion is 5 to 10 times more important than. So of course. But again, that gives you insight. If you train a network and then with and without, and you find out the network is better when you have motion, then that's nice, but it doesn't give you an understanding in this sense. I mean,
we have methods now to analyze.
Second?
There are many methods now to analyze what the network is.
I know that's what I think. No, that's what I mean, like. But what Jim DiCarlo started.
But is it worth? But he's doing a different thing, right? It's not.
No.
He's not working on. I think I've never. Maybe it's possibly work on visual latency and attention.
No. Of course not. No. But he's looking at whatever.
Anyway.
Yeah.
Anyway,
Yeah. So I okay. That's. I think. I mean, I am much. I'm not an engineer. I mean, I'm not interested in getting a machine working whatever 20% better than this. I want to have an understanding what's going on here, and I think I get that much more from if I construct a model and compare it with how well it performs in the task than if I run a machine learning algorithm and it does the job.
The vision people said for decades, and they got their ass kicked. You know. Yeah. No, it's true though.
But for example, you mentioned
said they were very beholden to handcrafted features because they put so much work into developing all these things, and as soon as they let the system learn, they basically got blown out of the water.
Well, performance-wise, yes, but I mean, you mentioned last night. You mentioned Dana Ballard. I mean, I think his insights. I mean, for example, Cornelia also mentioned with insight that in many cases you don't need to keep things in your memory because you just look at it, and that is true. And again, there's some wrinkles to it, but not always true. But I mean, I think that these are important things that we learn. At some point, if we just give up and say, okay, well, the problem can be solved with machine learning, I don't need to understand it, I think that's a loss. That's not science anymore. That's trying out different Python algorithms. Okay, anyway, I think we have to go on. Okay, so I'm going to skip. Oh, yeah, this is the system behavior. This is your task. The system does it the same way. You have feature pointing. Yeah, right. You have feature tasks. You have parallel performance. You have whatever. In the consumption task, you have increase and all that. That you can do this on real scenes, and we have done it. Many other people. This is by the way, we developed. It doesn't matter. We developed this method of testing the methods, and I think it's now the by far most used method to test computational modes of attention. You can use many different ways to do it. This one I skip because I want to come to limitations. Is the main limitation is that this is basic. This is completely bottom up. There's no top down, and you can have simple versions of top down. Is if you know you're looking for a red thing, you can change the weights in the color map, stuff like that. But it's still essentially bottom up. So that's a major limitation. I talked about the proto objects that I don't have time to talk about today because I wanted to do something about neuromorphic engineering. Skip over this, the papers. Sorry. So this is something that we published last December or November or something. So the question is, and this is work with a CEO who was at several Tellurites, but he's not here this year. And a student, Simone Shane, Sham, I guess. She was a student in Riyadh's lab, and that was a part of her PhD thesis. And I was visiting in his lab, and we studied it 5 years ago. So the question is, can we use neuromorphic hardware, CDS, and is there a way to get a science map out of there natively without having a C++ model, even a simple one, just taking the events? What is the shortcut to getting something that does a decent job as a science map? So, oops.
Just click on it.
Yeah. Oh, okay. This is unfortunate. Okay, so unfortunately, this is the. Remember this is I'm working on a PDF that was generated on the fly from a Impress Libre Express LibreOffice system. So this is actually, unfortunately, this is one change that matters because it shows you what you're doing there. So say in words what you're doing. So Camille took an ADIS, a DVS that has both a frame-based and a event-based output, and she put it different. I think that one I can show you. Yes, but these are videos, but not surprisingly, they don't work as a PDF. They put it in various places and recorded moving scenes. So this is rotating. This is people walking. This is a football. Fortunately, we don't have this here. Football at Telluride. So some people playing football, and then to use the black and white necessarily output from the frame output from the ADIS. And she had them viewed. So these are 8-second long videos, and there's I don't know 800 or something like that of them, all of them combined. And she had people come into the lab and then look at these videos, and she did eye-patting. Okay, as a ground truth where people are attending. And of course, we are confounding here over the tension. So just assume that where people are looking is where they are attending. We know it's 100% true, but it's mainly true. And some of the things that I skipped over show that it is actually true. And it's a good approximation though. So we get the ground truth where people are attending in this kind of scenes, and then we develop an algorithm to get a saliency output from it. And unfortunately, this is on this missing, on this the diagram is on the missing slide. But it's I think it's easy to explain. What you do is for every, so you have events, and events occur in a 2D XY plane and at a given time. So and at each time an event occurs, it has a space coordinate XY, a space coordinate T. And so what we do is we look back in history for a certain spatial interval and a certain time interval. So and it's very simple to do. We simply add up all events that occurred in this, if you want, in this brick-like structure that goes back, that is time, that is space, and that is time. We go back and then count all the events that occur. Okay, and that. And we do this on multiple scales. We have small and short and large and long, and we do this over different scales and then combine them, just as we did in the we basically sum them up with some normalization, because otherwise the small ones would not be weighted equally, and that's it. Okay, and we call this EVSD event. I don't know what it stands for, but this is all we do. Okay, just adding up events in the immediate history of every event, and we call that the saliency. Okay, and of course, well, proof is this is okay, that's what I've shown us earlier. This is the saccades and the fixations of one subject on the different. On the different scenes while they're doing the task.
Over so long?
Huh?
What is the time there? 8 seconds?
8 seconds, yes.
Over 8 seconds, the person only looked in this building scene on the bottom left. They literally only looked at, fixated on those points.
Yep. Yeah. When you see there's many more in whatever the Bastille, there's more people and all that. But in this case, there was probably a person walking or something like that.
Oh, I see. You don't see that.
So
you
the
don't
camera was always static. You had the PDF
Yes.
sensor, it was always static.
Absolutely.
Staring camera.
Yes.
So just the moving scenes. It looked.
It's yeah. Every scene, there are just natural scenes outside her office. Bastille is right next to the institute, so that's why they took Bastille.
Surveillance camera. Fixed camera.
Yeah, exactly. And people and birds and whatever this thing was turning, so it always moved. Of course, if you have no movement, then you have nothing. Yeah, that's really. So that's an important limitation, of course. So, and you could, I think there's an Avis color camera, something like that. But this isn't actually everything we get from this is only from motion, from not, I shouldn't say motion, from change in the scene. Yeah, that's absolutely right. So, and that is, I mean, I wasn't expecting that this would be a terrific result. What you get out of it, but surprisingly,
what is the result? Okay.
Yeah, exactly. Okay, so what did we compare it with? And we did not compare it with the deep learning things from Tübingen or something like that. We just compared it with the model that I explained with the only addition of a motion channel, because otherwise it would be very unfair to that model. So we added to the 3 channels that we had there. We added the motion channel, a very standard thing. Motion, spatial temporal motion energy, and we added also the one that I said I don't have to talk about, that was developed in collaboration with Ralph, Etienne's student, Etienne Cummings' student, Jamal Moulin, which was the much better, I think, model with proto-offset. So those were the 2 things we compared, and I'm sure, I mean, this is not as good as the performance is not as good as something that has been trained on videos. With 100 million parameters. So while we use the metrics, I don't think we have to go through that. And so here's the results. So this is the comparison for the 4 different.
We can't read it at all. We can't see anything.
Comparison of all metrics and models.
No, but we can't. It's too small.
Yeah, well, okay.
You have to zoom it. Yeah.
can I zoom on this? I don't think, I mean, really the only thing you have to, oh yeah.
Don't you compare to simple thresholding?
Okay, exactly. How did you do? Oh yeah, perfect. So does it work? So the only thing you have to look at, so there were 4 metrics, and in every one of them, let's say this one here, you have the 3 models. This is our new model. Then we have the new and shiny proto-object model, and we have the original ETR model that I talked about. And here you have for the different types of scenes, Bastille, foosball, and so on, you have the performance, and in all 4 metrics, higher is better. Okay, so and well, I'm not going to explain what the numbers mean, but what the only thing is important is it's a 1-bit information, and that is the best in each column. The best result, the highest result is bolded. Okay, so in this case, for example, NSS, the new model actually trumps the other 2. Oh, not a good word. Exceeds the other 2 for all of the classes. Here, it's not doing so well. It's actually none of them, but it's still. I mean, it's not. This one is 0.479. This one's 0.43. This one's 422, 425. So it's close. And here again, it's better than all of those. And here it's mixed bag. But it's compatible. I think we can say it's comparable. It's not like bottom of the barrel. And this costs you a DVS. You get it for it's entirely based on motion, but motion we know it's important. So this is what you get. And what else? So okay, so we have. So okay, this is detailed. I mean, how the tasks compare, or I should probably can I? Yeah. Yeah, this was a summary that shows the details over all the video numbers. We looked at the. You can take a simplified version of that. Let's skip over that. And I also, in the interest of time, I skipped over this. I just want to mention one more thing. So I presented this for the first time at the Bangalore Neuromorphic conference in January in this year, and I happened to sit next to Andre van Vleek, and so he heard the talk, and over he implemented the whole thing on his hardware that he brought, entirely neuromorphic hardware, and I'm embarrassed to say I don't know what it was, but it has some event-based thing, and he implemented the whole thing like in whatever 2 afternoons or something like that, just while we were sitting there and in the workroom. So it's basically salient for free.
Yes.
I mean, at least a decent approximation to salience for free. And yeah, well, there's many things here. You get ego motion. So Julie and I, we have been talking, actually last year, Telluride, we have been talking quite a bit about what to do ego motion. So that is certainly an important thing that needs to be addressed, at least for some. We could play with it and make it funny. Oh yeah, Piotr also made a version of his proprietary. It's not proprietary, but the things that he developed for many years. He also developed it actually in one night because he didn't get a student to do it. So he did an all-nighter and implemented this. So it's very, very straightforward to do. It's just counted. So and I think this is all I want to say, because I already went with my computer prompts. I went way over time. So
Thank you very much. Yeah, we can talk outside because we ran already.
Okay, thank you.
Now the Zoom meeting we're thinking. So right, so today is going to be a fairly different style of talk than the last one I gave. So the last one was focused on big picture, trying to build this large scale brain model and everything. Today I'm going to focus much more on specific work that's been going on in the lab, largely by my PhD student Graham Bamberger, who's actually at a different conference right now. And it's really, I would say, trying to address this general problem that I think neuromorphic engineers are interested in. And that's essentially building controllers that are fully neural, right? So the whole point of having this low power hardware is to be able to exploit it for all the variety of tasks we want to control is definitely one of those tasks, right? So the way we typically think about this is a motor control, but of course it can be controlled for anything at all, as is always wonderful about using control theory in general. So we take that to be a key desiderata, is building these fully neural controllers. And it's important to make sure that we can preserve the performance of the ones that work well, and ideally we can improve the power requirements by going into this fully neural representation. So I think there are kind of two key things about how we design these controllers. And one has to do with how we represent information over space, and the other has to do with how we represent information over time. And so I've sort of broken my talk down into two examples of looking for better ways to represent both of those things for particular types of controller design. So in some ways, this is going to be a fairly focused talk, right? I'm not going to be giving you like general methods for building any kind of controller whatsoever. It's going to be specifically looking at adaptive control and basically how to represent space to learn the function, the adaptation function, and then looking at MPC control and how to represent the temporal window that you're doing your optimization over during MPC. Yeah.
When you say power, is it power like electrical power or
Yeah.
power? Okay.
Energy.
Energy.
Yeah. Right. And so I think one key insight, or at least something that we've found a lot of the time, is that standard deep learning isn't enough. So trying to solve control problems by just gathering as much data as you could possibly need and then throwing it all into a big model generally runs into issues. And so I think I might give some examples of this. I'm not really going to focus on it at all, though. Hopefully that's, if not obvious, like a lot of you have run into it yourselves in the kind of controllers that you're trying to build. Maybe the most obvious way that this is true is when you go to things like adaptive control and your learning is all online, right? So at that point, you're going to have to change how you do your learning. So you could do stuff that's kind of like sort of standard deep learning, where you gather a bunch of data and then you backprop through the network. And then you have to be very careful about, switching your controller off for a while or letting the sort of weights get stale until you have enough data to update the weights and then changing all the weights out. Anyways, there's a lot of additional complexities that you'd have to worry about. Right. And so I think that this type of online adaptation is critical. And it's also, in our experience, a lot more performant to leverage control theoretic methods that people have already developed, right? Things like model predictive control. So you could, of course, just assume that you're going to get tons of data and off you go. But you could also use model predictive control or even PID control or whatever else, where we've learned a lot about how to build controllers for plants. All right, so one tool in our toolbox for trying to turn our controllers into fully neural controllers is this NEF that Terry talked about and I mentioned before. So I will just say this very quickly, right? That we can go from some high-level function, which we can think of as essentially our controller, like the standard way that we would write down a controller using modern control theory, and then basically compile that into a neural network, spiking or otherwise. And you can also use some of these methods that I sort of showed in the spawn model, where we use this for the vision system, where you can take a standard artificial neural network and convert it into a spiky neural network. So with these in our back pocket, it means that sort of if we can write the controller down, then as a dynamical system, which is how you write controllers, then we can build a neural network from it. Now, what this doesn't necessarily do is say how to represent that dynamical system in a way that makes this an effective compilation process, right? So one thing to be really clear, we call this a neural compiler, but unlike normal compilers, you are not guaranteed to get exactly the behavior that you described at the higher level, right? So there's basically approximations going on. And so that means that the sort of success of this is dependent on how you represent the high level system. And that's kind of what I'm talking about today, right? Is thinking not really at the neural level so much, but how do we represent things before we neuralize them, right? Put them through this kind of compiler. Right, so controllers typically are algebraic, but they're not always written in a way that's easy to make them neural. Yeah.
You're saying no, it's spiking.
Either one.
Yeah.
Yeah. So I'll show you some of each, right? But yeah, we don't generally distinguish between spiking and non-spiking unless we have like a specific platform that we're trying to target that's spiking in the case of building these controllers. All right, so a place that we started quite a while ago was by proposing a sort of general model for motor control in the mammalian brain. But of course, this can be thought of as just a general plant controller. But this is the kind of thing that basically describes the motor control system that is in Spawn, and that will preserve for the next one. And in some ways, it's pretty standard. So you think of yourself as having some plant, right, which is in this case the body that you're trying to control in some kind of task space, and the dimensionality of the task space in the plant can be different. So in the case of reaching, right, we're trying to get our current end effector position, right? So you can think of this as like our, I guess, in this slice 2D position. So from this 2D point to that 2D point, but of course we have to do it by controlling 3 joints. So we're going to have sort of these different numbers of dimensions, and you can write down the control problem by basically identifying the target that you're trying to get to, write down a standard proportional controller, then describe the sort of translation between the task space and the joint space, put on a differential controller, and then have this term which accounts for all the other stuff that you don't get by just having a P and a D term. Right, so usually what you would have is an I term. And one way to think about this adaptation sort of component to the controller is it's like doing your integration, but it's not linear, right? So it's kind of trying to learn what additional input do we need to put in the controller given where it currently is in the state space in order to drive you to the target. So you can think of it as accounting for sort of non-linearities that aren't captured well by the original linear controller, or you can think of it as, like I said, taking care of the I term for perturbations that you weren't otherwise expecting and so on. Right. Yeah, forget about the slow adaptation for now. So that would be if you actually, if you didn't know the parameters or the properties of your arm, so I'm not going to be talking about that today. But this sort of rapid adaptation where there's something about the dynamics of the system that you're controlling that you don't know is what we think of this U-adapt term as taking care of. So here's an example of building such a controller and then running it on a Loihi, doing a simple adaptive control task. So basically this arm doesn't know about the hammer that it's holding. I guess I should do Toby a favor and use this. So the arm doesn't know about the hammer that it's controlling. And you can see when it first reaches, it basically misses the target. This is little Santa Claus. Then, after a short period of time, it learns basically the additional forces that it needs to apply in order to get it to the target. Here, let me just start this again. Right. So at the very beginning here, it basically doesn't know about this hammer, and so it misses the target, right? So the hammer doesn't get very close. But you can see the adaptation happening here where it's basically correcting right now before I move the target. So now it's moving to a new target, but it's also having to correct for these same additional forces, these additional mass that's been attached to the arm, because this is a force-based controller. So if it doesn't know about the mass, then it's going to control improperly. And you can see with just a couple of movements, it does a pretty good job of getting to the target. And then what we're showing here is that after you do about 30 minutes of online training, basically it would act like it would if you had tuned the controller for having that mass on the arm. And then this down here, these are showing all the spikes or not all the spikes, some of the spikes that are being run in the part of the model that's learning to do that online adaptation. All right. So here we're showing a comparison of using this kind of adaptive control compared to sort of standard control, non-neural control methods. So one thing I will say is that you'll notice that I defined the controller as basically a PD controller plus an adaptive term. The adaptive term is going to be a neural network, right? So that's the thing that I'm actually going to focus on for most of the talk, saying like, how do we represent the sort of space that we're trying to learn that neural network over? You can, if you want, leave the P and the D components just implemented in algebra. What we did in that other controller is we embedded those using the neural engineering framework into a spiking neural network, right? So then the whole thing is a spiking neural network, and you can't really tell the difference between your adaptive and non-adaptive parts. And so what we're doing here is comparing this like sort of fully neuralized PD plus adaptive controller to other standard control techniques like LQR and so on. And so what this is doing is this is basically showing that we generate a random force field. You start with controllers which are good at controlling, so they can move the arm appropriately through the space. Then you introduce this unknown force field, and then you see how LQR handles the force field. And you can see that it has a really hard time, right? So optimal controller should look something like this. And here you can see with that reach model, right, where it's able to adapt to this change in the force field, that you get back to something that looks like fairly optimal control trajectories. Here we're showing the same sort of thing if you change the arm. So you basically make like one component of the arm longer than your mass matrix captures and your Jacobian. And then similarly, this reach model will learn. This is the part I said I wasn't really going to talk much about. And it also turns out that you are getting a lower control cost and greater efficiency compared to state of the art. So here's a bunch of types of controllers. So LQG, LQR, OSC, and a reach controller. Then this is an 8-bit quantized reach controller. And then these are showing the sort of control costs. So you can think of that as the accuracy. And then this is showing the amount of compute, so the number of flops running on a standard system. And we took the reach one, and then basically the reason we had quantized it to 8 bits is so we could put it on the Luigi and then do that demo that I showed you. And so again, what you can see is that the amount of compute that you have to do in order to implement these controllers is also much better once you've sort of done this neuralization, if you will.
What
Yeah.
is better in terms of cost compared to the one?
What is the cost?
No, why reach is better than the other one of cost?
Why reach is better than?
The baselines. So you said you have lower cost compared to the other one. Why?
Why is it a better controller?
Yeah.
So this is showing you what each of the tasks are, right? That it's a better controller for. So you can see it's actually not a better controller for just basic reaching. I guess this LQG one did not do very well, but for just basic reaching, it's not. But then for force field introduction, then you see some improvement. Actually, yeah, and the arm change. So these aren't enormously different between the operational space controller and the reach one. But yeah, basically these guys here are not able to handle those perturbations that I mentioned. Yeah. Yeah. All right. Okay, so for this neural adaptive control part, right? So yeah, just let me go back here and contextualize what the next slide is showing. Right, so what I was mentioning here is like when we're doing these different kinds of experiments, the thing that is making the reach model work better than these other ones is basically the fact that it has this adaptive component, right? It's got that U-adapt term. And that U-adapt term is the one where we're learning the forces that basically aren't accounted for once you do some kind of perturbation, put it in a force field, change the size of the arm and so on. So it really matters sort of how you set that neural network up to do the learning, how well it does. And so what we're going to be considering for the next couple of slides is how does it, how does that matter, right? So if I choose my neuron tuning curves in different kinds of ways, how does that affect my ability to learn in this type of adaptive control task? And most of these are just looking at things like building a controller that doesn't know about gravity and then putting it in a gravitational field, which is similar to adding a mass that it doesn't really know about. Right, so the learning basically happens by taking a bunch of tuning curves of the neurons and then weighting them in some way to, so you weight them and sum them. So you can think of the tuning curves of each of the neurons as a basis function. You weight the basis functions, you sum across them, and that defines a function over your space that you're now applying to the controller. And what you're really trying to do is learn that new function, which starts off kind of random. And so you can think of the components that are being added together, right? These tuning curves of the neurons, as their shape is going to make a difference for what types of functions you're good at or not so great at approximating. So the way that we write down our tuning curves in the NEF in general is to say that the activity of the neuron over the space X is going to be this is your neuron response function, right? So you can think of this as a leaking grid of fire or a Rayleigh kinase, whatever. And then we have these things that we call encoders, which you can think of as like a preferred direction in that space for this particular neuron. So these are like the input weights dotted with the point in the state space plus a bias, right? And so this is kind of a general way of representing a tuning curve. And so, if you take the space X, so let's say we're in a two-dimensional space, and we just take a leak integrating fire neuron, right? And we, give a preferred direction vector to that particular neuron. If we plot the tuning curve sort of sliced along its preferred direction vector, it will just look like this, right? It'll be this, the firing rate goes up as you go in some particular direction. So you might call this an on neuron. If you want the other direction, it will be an off neuron. And this is just showing that in the 2D space, there's going to be some particular direction where you get this type of shape. And then as you move away from its preferred direction, then you'll also have a roll off in the sensitivity of the neuron. So you can kind of think of it as like just a 2D sheet in the 2D space where the sheet is telling you the activity of the neuron given where you are in that space. Right, so the most natural thing to do is if you have a 2D problem that you're trying to solve is just to make your encoders equal to 2D. But then it means that you have a lot of these very broad tuning curves over the space. And what that means is that if your function has a lot of sort of locality to it, right, so it's very narrow over some parts of the space, you're not going to be able to do a very good job of representing the function using this type of tuning curve. So one trick you can do, right, is if you add a dimension to your sensitivity of your neurons, right, so now you are basically make your neurons three-dimensional, and then you project them down to a 2D space, you can make them sort of local in the 2D space, okay? So this is a little bit easier to imagine going from one dimension to 2 dimensions, but it's the same sort of principle, where you can think of sort of mapping your flat space into a sphere. And because you're on a sphere, then when you're sort of in your preferred direction vector and you move away from it, there's just going to be a small part of that sphere that's going to be sort of high when the input aligns with the preferred direction vector. And that means that your representation in the 2D space is very local, right? It's just like a little circle over the 2D part of the space. And so one of the things that we found early on when we were trying to learn these functions is that they had these kind of locality properties, right? You needed to be able to represent things fairly, with peaks and valleys all over the place, all over the space. And so one of the first things we did was exactly this kind of trick, right? You project it up into a dimension, and then you take your tuning curves, kind of project it back down to the two-dimensional space to be much more local. Right. So it's these encoders basically that are defining the tuning curves for us. And you can play with the dimensionality of those. And by making it go up one, you can make things a little bit more sort of local, like I was saying. And again, it's these sort of weight of whatever these tuning curves look like that's going to define the types of functions that you're able to represent. And I guess this point is just as a reminder, like the learning that we're doing here is online, and it's just a local error-driven Hebbian rule, so it's very easy to implement in most neuromorphic hardware, and it's biologically plausible because it's local and so on. So yeah, fairly straightforward type of learning. Right, and what this kind of trick shows us is basically that you can play with your neural representation of space in order to do a better or worse job of setting up the basis functions for representing whatever function you need in order to successfully accomplish the adaptation. And actually in the demo that I just showed, we're really just doing something like this, right? We're just kind of doing a projection up into a slightly higher dimensional space and then learning from there. So one other thing that is already maybe a bit familiar to you now, having been here and heard about this a couple of times, are these spatial semantic pointers. And you can think of this as another way of projecting up into a space, but it's much, much higher dimensional than just like D+1, right? So the semantic pointers typically, oh, I didn't write the equation. Oh, I did, okay, good. So the semantic pointers, as you know, I guess, as we do things like basically pick a high dimensional axis vector and then convolve it however many times we need to represent being at some particular point in a continuous space X. And if you want to do it for X and Y, then you have an axis vector for X and an axis vector for Y, and you put them to the power, this convolutional power of your XY location. And then that basically gives you a representation of that particular point in space, right? So if you think about it, this is kind of an extreme version of that D+1, right? So now we're working in like 100 dimensions or 200 dimensions. So it's like for representing a 2D space, so it's like D plus 198, where we have two axis vectors, one for X and one for Y, and then we put them to the power of the XY locations and then bind them together. Right, so this is writing that out. And so what you can see is that when you sort of represent these X and Y locations, and if you sum them together, then you basically get, those very local functions, right? And you can play with the parameters and dimensionality and so on in order to control the width of those functions. So the thing on the right here is showing basically what happens if you add two of these things together down to some arbitrary object. So, this would be one of your representations, this would be another one of your representations. But in general, what it's telling you is that you can, and this kind of decoding, right? So the representation, just to be really clear, the representation you have is just a 200-dimensional vector. And then to sort of see what it looks like back in the two-dimensional space that you've encoded, we take that 200-dimensional vector and then take the dot product of it with every possible encoding of every position in space. So this is not a thing you'd ever do, but it's a good for visualization. And so that tells you kind of like how local is your representation of that point in space in your vector representation. So I don't know if this helps, but the previous visualization I kind of showed a sphere, and you can see that like a big chunk of the sphere would have kind of lit up if we only went to D+1. So here we can see that this is much more localized as we go into these higher dimensional spaces. Right. I want to talk about this. I think this was sort of covered by Nicole. Right, so this now is giving us a little bit clearer picture of what happens as we change D as we're trying to represent some particular point, right? So here we're just looking at the representation of X, and you can see if D is too small, then you have actually kind of a terrible representation where you can't really tell if it's here or any of these other lobes. As we increase D, then you can actually prove that this function approaches a sinc function. So you get something that really is quite local, but it's going to have these sort of ringing properties on the sides as well. And then you can change the scale parameter to basically scale that with respect to the size of the space that you're trying to encode. All right. So in this work, basically when we noticed that and thought about back to our adaptive control stuff, so these two things were completely separate for quite a long time. But then we sort of got a better understanding of the SSPs and realized that what they're doing is essentially this sort of very localized representation. And so we thought, well, maybe that will improve the adaptive control, because we had already discovered that introducing some amount of locality was important for learning the functions that these controllers tended to need, at least for the arm reaching case. So in this paper, we basically looked at a whole bunch of neurally inspired representations or basis functions, if you will, right? So this is basically a bunch of different types of encoding. And we kind of named them after the different types of neurons that they look like. So here we just have a completely random projections. Here we have what we call selected. So these are ones where we've kind of done that D+1 thing and then gone and tried to pick neurons that are responsive mostly to just one part of the space. These sort of Kenyan cells, these are a random SSP, and then an encoder for each cell, which is just a random projection onto the hypersphere. These place cells are sort of the random SSPs, which you can think of as the ones that I was just showing before, right? So if this looks like this peaks kind of at one location in space. And then last we have these hex SSPs, where it looks a lot more like a hex cell encoding of some kind. So each neuron, is kind of sensitive to lots of different parts at different frequencies, but when you sum them all together or look across the entire population, you can get fairly localized representations. So essentially what we're going to do now is just run a bunch of experiments with the same adaptive controller using these different types of sort of neuron tuning curves, or basically you can think of these as also like the input weights, and see which of them works best for doing neural control. Right. So it's a 3-length arm in a 2D space. So that's the plant that we're using. And then the kinds of perturbations we're doing is we're adding an additional mass, or we're adding just kind of like a force field throughout the space. So kind of like the experiment that I showed before. And then we've got some results. So these are the 2 different experiments: the additional force and the additional mass and the forcing function. And you can see that, you know, they're actually generally fairly similar-ish, but in both cases, those place cell type of representations were the best of the ones that we tried. This is just showing an example of kind of what the runs looked like while we were doing these experiments. So you can see these are all running in spiky neurons. And so with a random encoding, you're sort of controlling your 2-length arm through a circle, and then you introduce a perturbation, and then you can see that it starts to kind of get back to the original, but doesn't get there very quickly. And in contrast with the SSP place coding, so this is the one that worked quite well, you can see that it actually gets back pretty fast. And one of the reasons that I think it's useful to look at the actual performance is because this type of difference in accuracy looks a lot more compelling than everything being 10 to the -2 and in about the same order, right? Which is something that you often find in control, where if you kind of look at the metrics, they can be close-ish, but when you look at the behavior, they can often be a difference between success and failure in some cases. All right. Okay, so yeah, so you know, from a quantitative perspective, we found that these particular way of representing space using these random SSPs, or these place cell-like representations, was the most effective. We've also shown, so we didn't have a lot of like other types of methods for representing positions in space in this particular paper, but in other work, we've looked at how SSPs compare to radio basis functions, one-hot representation, tile code, and so on. And you can show that in general, the SSPs are better. The hex SSPs are also good. One interesting difference between hex SSPs and rand SSPs is that the hex cells are not restrictive, in the sense of you don't have to make a specific assumption about the size of your, or a less restrictive assumption about the size of your operating space. And this is partly because these are defined essentially with cyclic bounds, whereas the way that we were picking the rand SSPs, they were not, right? So we had a very sort of strict set of limitations on what would happen if you went outside these bounds, and basically things would just fail. Whereas in the SSP space, if you go outside of the expected bounds, then you'll get something that kind of is a repeat of what you had inside the bounds, right? So you'll at least have some reasonable representation. Right, both were stable, and in the paper we actually prove the stability, and we use a biologically plausible learning rule. Right, and this is also just saying that the previous best way was using these like selected neurons, where we just did the T+1 and then use some other techniques to try to pick things that were fairly local-ish. But as you can see from those graphs, they're not that local. And both of these did significantly better than that sort of best previous method. Okay, actually, maybe if anyone has questions about what I've talked about up till now, now's a great time to ask, because I'm going to switch over to the model predictive control stuff. Any questions on the space representation? All right. Yeah, and actually, this might be worth highlighting, but one thing that might not be obvious when you see people give talks about that adaptive control stuff is it is super easy to implement, right? You don't really have to understand what's going on. All you need to do is you need to build a PD controller, and then you take a neural network, you take the state of the system, you put it into the neural network, you take the output of the PD controller, put that into the neural network for the error signal, and then you add the output of the error of the neural network and the PD controller together, and that's your adaptive controller, right? So it is like, very few lines of code, and something like Nengo, it takes kind of like 4 lines to build an adaptive controller. So if you ever have something that looks like you wish you had adaptation, this is a really easy first thing to try. It might not be the best all the time, but yeah, highly recommended to just give it a whirl. All right, so with that comment, I will continue on. Right, so in model predictive control, so here, future work, we're trying to sort of think about adaptation in the way that I was just talking about, but it's actually quite a bit more complicated. But model predictive control, sort of as an algorithm, has some significant challenges for it. One of those is, or the main one in some ways, is basically running the optimization problem, right? So in this case, you are essentially looking over time, right? How is my system going to behave given particular types of input? And you make that prediction by having a model, right? And saying, now, how you represent time can make a big difference to how much compute it takes for you to perform the optimization problem of saying, okay, if I try this particular trajectory, how well do I do? If I try this other trajectory, how well do I do? And you're basically asking that question as much as you possibly can at every moment in time. So one thing we can think about is, like, can we restructure the way that we represent space and use a neural network as the model, basically, and save on the optimization time while ideally preserving performance. So this is the kind of thing that we're looking at in this work. Right, as I think has come up a little bit before, we, in other work, again, we were kind of looking at how to represent information over time, and we came up with this Legendre memory unit. So, this is like a standard state space model where you've got this sort of linear dynamical system that is, representing time. Basically, it's like taking all the input over your time series and compressing it in some interesting way, and then you compute some nonlinear function of that. And in some ways, we're taking those same types of methods and applying them here in this model predictive control case. But I think it's important to emphasize that in the model predictive control case, we're actually not running things over time, right? We're just using the representation of time that the LMU helped us discover to try to improve the efficiency. One nice thing about the LMU is that it was, oh, I said most of these things. Oh, well, anyways, so the one thing I don't have on here, which maybe it's on the next slide, is that we basically discovered this by trying to understand time cells in the brain, right? So the LMU itself is, sort of independent of neural representation or like how brains function per se. But the fact that it has this kind of like dynamical system embedded inside these nonlinearities made it a surprisingly good model of these time cells, which people discovered in about 2014. And if you haven't heard of those, they're very analogous to place cells, but over time. So we're going to basically use these same types of representations, but in this other context of representing time for performing an optimization problem. All right. Okay, so actually, I guess, yeah. To give you a sense of what the LMU representation is doing, there we go. I actually didn't get my order right. So what the LMU is trying to do basically is solve this problem of representing information over time, right? So suppose that my output is equal to my input delayed by some amount theta. This turns out to be an infinitely difficult problem if you don't say anything about the frequency content of your signal, right? Because if you allow arbitrary frequency, then you basically have an arbitrary amount of information that you're trying to store for however long your period theta is. So the interesting thing is that this, turns out to be a linear system, and you can write it in the Laplace domain this way. And basically, this is what tells you that this is an irrational or like an infinitely difficult problem to solve in some ways. So what the LMU does is it basically says, well, what is the optimal rational representation? So we're going to build a causal system with some finite number of states that can represent this function e to the negative theta s. And there turns out to be theory that mathematicians have derived, basically telling you how to get the optimal rational representation of any irrational function. And this is called using something called the Pade approximates. So when you use those, then you can basically derive what this system is, and then you can transform it into your standard modern control theorem expression for the transfer function. And this basically lets you derive what these matrices are that are going to implement that optimal dynamical system for representing information over time. Right. And when you do this, so basically when you solve that problem and you generate, maybe I should, right? Oh, okay, twice. And when you generate this last equation that I had here, basically what you find is that this C matrix, so this is basically something that is taking you from your state space representation back to the time domain. That rows of that C matrix look like the Legendre basis, right? So I think this might have been an accident or like an unfortunate decision on our part to call this a Legendre memory unit, because a lot of people are under the impression that we kind of picked the Legendre basis and then saw what it did. But that's actually not what happened. We solved this optimality problem, right? So trying to represent delay. And then we found that it happened to be the case that the dynamical system was projecting the signal over time into a bunch of coefficients, which were decodable by a Legendre basis, right? So the basis came second, which I think is not irrelevant and kind of interesting. So specifically, this Legendre basis is shifted and scaled, so you can see it's causal, right? So usually you define the Legendre basis with 0 in the middle and so on. And it's scaled to make it behave better numerically, and basically put equal weight on all the different dimensions. But when you now run this, you can do a very good job of delay. So basically, the input for this dynamical system here is the blue line. The ideal output is the green line, and the Legendre memory unit using 6 dimensions is the dashed blue line, right? So this is like band limited 15 hertz noise, white noise. And you can see that it's like on these graphs, it's basically indistinguishable from the correct answer. And then you can also plot all of the 6 coefficients, right? So this is projected from a one-dimensional signal into a 6-dimensional space. So you can actually look at the dynamics of all 6 dimensions as well. You can take this system, this 6-dimensional system, and using the NEF, basically we wrote down a dynamical system. So now we can just embed it into a bunch of neurons. And so this is sort of showing the activity level of 1,000 neurons where we've embedded this dynamical system into. And then we can compare the sort of tuning properties of the cells to the data, right? So this is like the time cell data that people have published. This particular data set comes from some experiments done in the hippocampus. And you can see that basically with one free parameter, so that number 6, right, is a free parameter. It's like the order of the approximation of the optimal delay that you're using. So with one number 6, we can do a fairly good job of capturing, this distribution of tuning curves that you see, where basically they get sort of moved out in time, and as they get moved out in time, they also get wider. This is kind of like the 2 main characteristics that the neuroscientists noticed about the properties of these time cells. And then this is kind of just looking at sort of correlations over time, and you can see things are a little bit cleaner or significantly cleaner in the model case, but it does turn out to be a fairly good match. Yeah.
Just like a more mechanistically, what does this dynamical system actually looks like? Like you showed on a very abstract level, like there's a matrix C, but doesn't have a specific structure. Like, can you build?
Yes, actually, so yeah, so I mean, I don't think I have any pictures here, but yeah, so the matrices that are important are the A and the B matrices. So those are the things that are actually taking the input and projecting it into the space. That's the B matrix. And then the A matrix is computing the dynamics. So that's like determining how to update this system state over time. So the A matrix is very structured, right? And this is like the reason that state space models are effective and efficient is because you have structure in that A matrix, right? And so it's maybe unfortunate that I didn't show a picture of what it looks like here. But yeah, you've got a lot of zeros all over the place. You can compute the values of each of the sort of values that are non-zero in the matrix just using a couple of equations. So it turns out to be like order n instead of n squared when you're trying to compute it and so on. But yeah, I can send you papers or things if you'd like to more about that. Right. Okay. Right. So returning to the world of model predictive control. Yes, I should. Toby's not even here to yell at me, but right. So standard model predictive control. Actually, this would be easier. You can kind of see that. All right. So standard model predictive controls, we have some cost function that we're trying to minimize by picking a trajectory u, which is going to, give us the best performance, basically. And this is going to be subject to some constraints like the dynamics of the system, the initial conditions, and a bunch of other potential constraints, S. And we're going to write our cost function out as in a sort of standard term where we have like state cost and we have a control cost. So this is the way that we would typically write this out. If the system is linear, then you can kind of solve this super efficiently. But as soon as it's not, then you can't. You basically have to be running a bunch of sample trajectories U, and then computing the costs, trying another sample trajectory U, compute the cost, and so on, given your model F that you've implemented in some way. So essentially, what we are proposing here is to sort of recast the problem into this Legendre space, right? So we call it Legendre, model predictive control. So basically, we're taking our states over whatever window that we're trying to do our prediction, and projecting them into the Legendre basis, right? So what we're doing is we're taking our original time varying signal X and basically finding the coefficients P that are going to be, when multiplied by the Legendre basis, let us reproduce the value of X. So we're representing our states over time, basically now with just a set of coefficients P. And so the idea here is that we can have way fewer P's than we would have had time points in the original X. So then we can do the same kind of projections on our, or we can use those same sort of coefficients to project our two cost matrices Q and R, and then turn our cost function basically into what I've got written down here, where now we have this new cost function to evaluate, but we've put it into a representation over Legendre polynomials just using a bunch of coefficients. So essentially, the reason that we kind of came up with the LMU in the first place was to compress information over time. The representation it discovered was Legendre polynomials, meaning that it's good at compressing information over time, sequential information. And so we thought it would be interesting to try using that same representation here. And in the past, people have tried other basis functions. So this idea of just like representing a time signal with a basis function, as you can imagine, is not a new one. But we did find that the Legendre polynomials worked better than other types of basis functions. So the other part to this, of course, is computing that function f. So this is the actual model. And what we did here is, maybe what anybody with a neural network would do, right? So you basically take the neural network, you take a bunch of representations over time and initial conditions, you train your neural network to figure out what the states would be given the input. So the input here is your control trajectory, and then the output is the state of the plant. And you generate a whole ton of data over this space that you're interested in. You use backprop to learn the neural network, and then you use that as your dynamics model, right? So nothing particularly novel there. Right. And so the network that we're using here is very simple. It's a single layer. There's about 23,000 parameters in the final version. I show you some data from other ones with only about 10,000 parameters. So these are very small networks. And we're using about 400,000 training samples. And one nice thing, of course, is that we can generate as much data as we want because we're doing this all in simulation. And in particular, we picked this simple cart pole problem. But you can see sort of right away that using a neural network to predict the trajectory of the cart pole, given some control input, you can see a sort of immediate advantage to using the Legendre representation over, this is just in terms of mean squared error, over representing everything in time, right? So this time one would be basically, I can build a neural network that does exactly the same thing where my input is time, right? Like I've sampled at every moment what my control trajectory is. I can put that into a neural network and it can predict the temporal trajectory of the state. And so that's what the blue line is, right? But then you can also do this kind of compression thing. And this order is that parameter that was 6 in the examples that we saw before, right? So this is just sort of the amount of number of Legendre polynomials that you're using to represent things. And you can see actually at really high orders, you get a bunch of error, probably numerical error. But for most of them in general, for window lengths that are anywhere past about 100 milliseconds, they do about the same. And this, of course, is also going to have to do with like the frequency content of the particular control signals that you're looking at and so on, which is probably what we're really being told there. But the more important thing is that you have this general advantage in terms of RMS error once you switch to this representation of time. Right, so the representation helps. And then the last thing I want to leave you with is basically applying it to that simple problem, and then also introducing constraints. So if you remember in the original formulation, we had S with a bunch of constraints. So in the initial formulation, we just had no constraints. So here we're looking at two particular types of control inputs. So one is step function, and the other is kind of like following a oscillatory input. And you can see it does a reasonably good job, right? So especially in oscillation case, it's doing a fairly good job of tracking. In this case, you can see that it does an okay job of tracking, but then there's this fixed error, right? The kind of thing that you would typically get rid of with like your integral term. But we then also introduce terminal and control constraints. So control constraints, limiting how much input you can actually put into the system, and then terminal constraints, meaning that you want to be basically enforcing doing something that's kind of like taking the place of the integral term, right? Forcing your constraints to go to zero. And anyways, yeah, I won't get into the details. So the thing that sort of is most important from doing this is basically looking at how it compares to doing the same kind of thing, but in the time domain, right? So running this standard type of model predictive control optimization. And the thing that we see here is a fairly significant reduction in the amount of compute, which we see as a speed up in how long it basically takes us to perform the optimization. And then, yeah, across the step function and the sine wave, you have sort of similar speed ups. And these are both in the case where we've actually implemented these additional constraints to get the performance to be a little bit better. All right, so that kind of concludes the sort of two things I wanted to talk about. So one is thinking about representing space, or in this case, the sort of the state space of the controller in order to do a better job of adaptive control. And so we saw that using these place cell-like spatial semantic pointers are helpful for doing that. And then in this definitely super simple example that we looked at so far in MPC, so it's very early days for doing this MPC stuff. But we did find some advantage to using these representations that are kind of like what we think time cells are doing in the brain in order to improve the efficiency of doing our model optimization. So yeah, just to emphasize, definitely early days. There's lots more to try. Scaling things up in terms of complexity, looking at more sophisticated types of controllers. So trying to marry the adaptation with the model predictive control, so you can basically learn on the fly to improve your model, and so on. So there's definitely lots more things to try. And the next thing that we're going to be doing with the MPC is basically vehicle control. So a more interesting and challenging control problem, but it's going reasonably well so far. And I will stop there. So thank you. Any questions? Yep.
I think you were saying that the network control is actually more efficient than doing the kind of like the analytical solution for some of the early examples. I was a bit confused about this because I'm assuming like if you have kind of a low dimensional problem, then computing some, I don't know, like whatever functions you need to compute is probably cheaper than computing a lot of nonlinearities for the neuron. So I'm kind of wondering what your intuition is, like why the network is more efficient.
This is a tiny neural network. Right. It's super cheap, right? So it's one layer. There's like a couple hundred neurons, so it's not very many nonlinearities. Everything was being run on a CPU, right? So just to make it all sort of consistent. But yeah, it's just because basically doing the optimization over like every point in the time window is just a lot more expensive. Like if you think about it, so for like 1 second time window with a sample of 1 millisecond, right? You've got 1,000 time samples and you have 5 Legendre polynomials, right? So that difference in scale is really quite enormous. So yeah, I think that's why.
When you say one layer, do you mean in Mango as in a population, or do you mean as in? So the population has different dynamic, like different connection paths in it, or not just a traditional?
No, in Mango, a population has no connections in it until you add something in. So I literally mean one feed forward layer with no recurrence. Yeah, which is the same as like one feed forward layer in PyTorch or whatever. Yeah.
question.
Sure.
This, like there's this slightly controversial topic about like spikes, no spikes, and so on. You kind of, I think you said at the beginning you don't really care that much because the framework works for either case.
Yeah.
I was just wondering if you've ever looked into like with various bars spiking out, could you do something like bang bang control or something like event-based control? I mean, I assume it would be a slightly different framework, but I'm just curious if you have tried this or if you know anyone who has tried this.
So we have not tried it. I also don't know of anyone who's tried it, but I'm also not super well versed in the field. But yeah, and I like maybe just to put a little finer point on my comments about spike versus no spike, like essentially the difference for us is one of matching the hardware that you're going to be running the thing on, right? So like I think it's pretty much always been the case when we've done it and we've built a spiking neural network to run on like neuromorphic hardware, the power numbers are better, right? And so ultimately it's worth having it in spikes. You often pay some kind of accuracy costs, and there are various ways of dealing with that and so on, of course. But yeah, usually we try to make things the same performance. The amount of number of parameters and so on can vary slightly, but then you look at the compute and the energy per computes for the amount of compute that you're doing. And in every case, we've looked at like the neuromorphic stuff has been cheaper. So the way that we interpret that, or at least I typically interpret that, is once I know what the algorithm is that I think is going to do a really good job, then if I care about power, and often we don't, right? It's just very application dependent and grant dependent and all this kind of stuff, collaborator dependent. Then we will, use these methods in order to put things into spikes and all that kind of stuff. So it feels a little bit more like an engineering step after we've discovered what we think is an efficient algorithm in general in the non-spiking world. Yeah.
But for you, it's a little bit more like a variable precision that you can, like a knob that you can.
Yeah. And actually, that's fine. I have to make this comment now because I was making noises, but we often find that variable precision, really multi-bit spikes often turn out to be the best. So a lot of people, when they do spiking, they think about 1-bit spikes. Hardware fairly naturally lets you do multi-bit spikes, like you're sending packages around anyways, more than 1 bit. And we've often found that actually multi-bit spikes is typically the best. And but the multi-bits is usually less than 4, right? So it's kind of in this gray area. Anyways.
Hashtag ad, hashtag leaving.
There you go. Any other questions? All right. Well, if not, then thanks for your time.